All right, so what we're going to show now is that the Riemannian Hessian operator is going to be related in some way, shape, or form to the Euclidean Hessian of related function, which is expressed in terms of the Riemannian exponential. Okay, so we'll show that the Riemannian Hessian is related to the Euclidean Hessian, well, actually coincides actually with the Euclidean Hessian of a function which involves the Riemannian exponential. Okay. All right, so how are we going to go about doing that? So let me state the proposition as follows. Okay, so let M be a Riemannian manifold. And F a real valued function on M. Okay, then the following is true. That the Hessian of f of x, right, is defined to be just the Hessian of f composed with the exponential at the point x at the 0 about x. Okay, so let's think about that for a second, right? So f is a map from okay, so you have the manifold, you have the rails. F is a map from the manifold to the rails, right? And then of course we have the exponential at x, right? This is mapped from tx of m to that. All right. So you now have a map from tx of m to the rails, right? Tx of m, of course, is just a Euclidean space. All right. So it makes sense then that if you have a sort of essentially, you know, it's like, again, a map, it's like from a vector space, it's like a scalar value function. It's like on a vector space, you can look at the Hessian, the classical Euclidean Hessian on that, all right? To give you now a linear operator from TXM to itself, right? So that's what the equality is. This is an equality at the level of linear operators on TXM. Okay, all right, anyway, so let me just finish off this. This is true for all x on the manifold M, right? And then, so where hash of f of x denotes the Riemannian exponential, sorry, the Riemannian Hessian. And Hess of f composed with the exponential at the point 0x denotes the Euclidean Hessian. Okay. And sort of TXM is endowed with the inner product defined by the Riemannian structure. On M. Okay, so of course you can try to prove this. It's like using local coordinates and then using the fact that, so actually let me rephrase that. You can prove this. It's like by using sort of Riemannian normal coordinates, which if you recall is the coordinate system which is induced by the exponential, okay, or more precisely maybe the logarithm of this. The advantage, if you will, it's like of normal coordinates is that the Christoffel symbols vanish, and so that sort of makes life very, very easy. Okay, so let me just sort of say that. So this can be easily proved, right? Sort of by working in normal coordinates. And using the fact that the Christoffel symbols vanish in these coordinates. Okay, and if you will, it's like this is nothing more than f composed to the exponential. It's like of x is essentially nothing more than the coordinate representation. It's like of the function, if you will, of the function f. Okay, so what we oftentimes denote by f hat. Okay, so we're not going to do this. It's like we're going to try to prove this in a slightly more abstract way without using, it's like without using coordinates, and let's see what happens. Okay. So again, what we want to show is that this thing agrees as operators, right? So what we need to show is the following. We want to show that Hess f of x, okay, paired with, applied to one vector, paired with a second vector, right, is equal to this. Okay, so you want to show the following. Okay, so let's try to do that. Okay, and I guess you have to do this for all vectors in Txm. Okay. All right. So so let me go ahead and try to do that. And let me sort of make the following observation. So we had already previously proved that the Riemannian Hessian operator is symmetric. Okay. So what's nice, and of course it's a linear operator. Okay. So so it turns out that you can prove this. It's like with by just showing this, it's like for it's like both of these vectors being the same. So of course that simplifies matters quite substantially. And the reason for this is the following. So you observe the following, that by the polarization identity, right, any symmetric linear operator let's call it B, right, satisfies the following. Okay, so 2 times B applied to these two vectors. I should say that this is true for a bilinear operator, right, is equal to B applied to the sum of these two vectors twice minus b applied to just the first vector twice minus b applied to the second vector twice. Okay, so you can just use bilinearity, right? So this is b of this and this plus, I'm just going to expand this, right? Okay, so these four terms correspond to expanding this first term. It's like using bilinearity, and you subtract off the first one and the second one, right? So this cancels this cancels this, and then you're left with two of these. It's like, but if you have that this operator is symmetric, it's like, then of course that's equal to 2 times that. Okay, so that's sort of a relatively straightforward calculation. Okay, but the important part, right, is that if you look at this left-hand side, right, it's saying that, well, you know, it's like this pairing, right, between, okay, this operator, it's like acting on sort of two vectors, right, can be expressed in terms of the operator acting on a bunch of different, it's like vectors, but where both terms are the same, right? So bottom line is the following. Okay, if you want to show that this equality holds, right, you just have to show it. It's like for you know, it's like where the two vectors are the same. Okay. All right. So that's where we're going to proceed from here. Okay. So therefore, since we already showed that this operator is symmetric, it suffices to show that so that Hessian f of x in cos c paired with cos c is equal to Hessian of f composed with the exponential at 0x. Okay, applied to cos c paired with cos c is that. And this has to be true for all cos c in the tangent space at x to m. Okay. All right. So the right-hand side of this thing, right, just involves the classical Euclidean Hessian, right? So our right-hand side just involves the classical or Euclidean Hessian. Okay, so I can expand that. Okay, so the Hessian f composed with the exponential at x sort of expanded around the zero vector. Right, this is just equal to d squared dt squared f composed with the exponential at x of t times cos c evaluated at t equals to 0. Okay, so this is d dt of f exponential x t cos c. Right, this is of course nothing more than a now a scale valued function, right, which you can take the second derivative of. Again, evaluated at t equals to 0. Okay, and so this is d dt of df exponential x of t cos c in this direction, d dt exponential of x of t cos c. again evaluated equals to 0. All right, and then this term here is nothing more than the gradient, or it's related to the gradient. Okay, so let me maybe write that down. So this is equal to d dt of the gradient of f evaluated at the point exponential x t cos c paired with d dt exponential x t cos c evaluated at t equals to 0. Okay. All right. And then what we're going to do is we're going to use the invariance property of the sort of this Riemannian metric. So by the invariance property of the Riemannian metric, okay, that expression is equal to d dt of the gradient of f exponential x t cos c paired with this vector field, or vector, sorry, plus the gradient of f at x paired with d squared dt squared exponential x t cos c. Then by the property of the exponential, this second term vanishes. Actually, by the definition. Right, because if you recall, it's like the exponential map in some sense is related to sort of acceleration-free curves, right? So this second derivative, it's like vanishes. Okay, and then the other property is that it has to do with essentially the d dt of the exponential. Okay, so d dt of the exponential at x of t cos c equals to 0 is equal to cos c. Okay, and this just comes from the fact that the exponential map is defined as the solution of an initial value problem, right, where the vector field is really just this this vector field here. Okay, so all right, with those two observations in mind, then this right-hand side of this expression, right, reduces to just the covariant derivative of the gradient of f, okay, paired with cos c. All right, and of course this is exactly the Riemannian Hessian, right? So that's what we need to prove. So we proved this. It's like for where the two vector fields are equal, and again, it's like by the polarization property. It's like for symmetric linear bilinear operators, right? This it's all that's necessary is to prove this. It's like for where the two vectors are the same. Okay. All right. So yeah. So that's what happens. It's like when you have the Riemannian exponential, and then what we'll show next is that similar results hold. It's if you instead of having a Riemannian exponential, you have a retraction instead. So let me just stop here for now.